answer is C. Let me show you how we go about this. So when you have the positive charge that comes up close here, you get negative charges here and positive charges here, because all those negative charges rush over to the blue conductor. All right, and then when you take the wire away, you get negative and positive, and so the final charges are negative and positive, which is C. Is that charged by conduction or induction? It's induction, right? It didn't require contact between the two charged objects. It's induction. All right, we'll come back to this. Let's do Coulomb's law. All right, Coulomb's law, it's going to be very similar to Newton's law of gravitation. They're the same form. They're both an inverse square law. If you recall Newton's law of gravitation, that was the force between two masses. It was G m1 m2 over r squared. But Coulomb's law, it's very similar. Coulomb's law says that the force between two charged objects is K, I'll give you the value for that in just a second, times Q1 times Q2 over r squared. Both of them have this inverse square law. It's because these are field forces that emanate out in a spherical way, and so it works out that the force is proportional to 1 over r squared, because it emanates out into 3 dimensions of space in a spherical way. K is our Coulomb's constant. Oh, and by the way, this, you don't deal with individual charges very often. Some of you maybe one day you'll deal with individual charges in the way that you model things in graduate school or whatever. But it becomes very important when we develop the idea of electric fields and also electric potential. And that is of crucial importance when we're dealing with just everyday electrical circuits. So we'll build upon this in the next chapter when we start talking about electric fields and electric potential, which becomes more applicable to sort of everyday life. So anyway, Coulomb's constant is, we call it K, and it's equal to 9 times 10 to the 9th. It has units of newtons, meters squared per Coulomb squared. I won't use it in this way, but Coulomb's constant is equal to, this is just an aside, you might see this elsewhere, not in this class though, is equal to 1 over 4 pi epsilon naught, where epsilon naught is the permittivity constant. But that's just an aside. You don't need to. Okay, Q is in units of coulombs. So we'll use the SI unit for that. R is in units of meters. However, a coulomb of charge is a really big charge, and a meter is a really big distance when you talk about charges being separated. Usually the charges are going to be much smaller and much closer. So I just want to remind you of our metric prefixes, in particular these metric prefixes, because we'll use them quite a bit. Does anybody remember what micro is? 10 to the what? Right, -6, and nano, right, is -9. I always remember nano because it looks like 9, right? You just change the A to an I and the O to an E, and that looks like -9. So you'll need to know those. You'll need to know all the metric prefixes too, just to remind you the ones that you're responsible for. On the big end are giga, mega, this is 10 to the 9th, 10 to the 6th, kilo, 10 to the 3rd. These will become more important when we get into light, because we'll look at the frequencies of light, which have very large frequencies, gigahertz and megahertz. And then on the other side we have centi, which is 10 to the -2, milli, 10 to the -3, micro, and nano, 10 to the -6, 10 to the -9. All right. You'll need to do unit conversions. We're not going to do that here, but you'll need to know how to convert between the different units, which we did last semester. So if you're having trouble with that, if you still have trouble with it, just come see me. We'll work it out. Okay? Let's see. Coulomb's law, as I said, is similar to Newton's law of gravitation. They're so similar because they're both field forces. So we'll draw some parallels later as well when we're developing the idea of potential. Remember, we said that field forces are something special. They have a special word that describes them. Does anybody remember what that word was? What are field forces? What type of force are they? Field forces? No. But you're in the field forces are involved in elastic collisions. Yes, that's correct. But what was it that they did? Field forces. I think Rush Limbaugh, maybe? They're conservative forces, so field forces are conservative. So electric forces are also conservative, and that'll become very important, as I said, when we develop the idea for potential. You don't need to write that down now, we'll write it down later. Okay, so just like with Newton's law of gravitation, the third law also applies for field forces. So if I have a force on charge 1 that's due to charge 2, what's going to be the direction of the force on charge 1, left or right? Yeah, left, or away from charge 2. So the force on charge 1 due to charge 2 will be in that direction, and the force on charge 2 due to charge 1 will be in that direction. And Newton's third law says in these field forces that when I have one force, that I have an equal but opposite force. So F12 is equal to the negative of F21. That applies for all forces, but particularly it applies for field forces. And then similarly here, I would have F12 in this direction and F21 in this direction, and the same would hold true, that F12 would equal the negative of F21. By the way, with Coulomb's law, F equals K Q1 Q2 over R squared. Notice that I didn't write any arrows. Yeah, Rob. Mm-hmm. It will, right. Yeah, so you'll see that we're going to do some vector problems, but yeah, so F12 would be in the negative x direction.
So wouldn't it be negative F12 equals positive?
No, because F12 is, I mean, you could write it that way, but F12 is negative and F21 is positive, so F12 is the negative of F21. Or you could say F21 is the negative of F12. Those are the same statements.
Okay.
Right. So here, when I write Coulomb's law, that's a good question. It'll come up next section. Here, when we write Coulomb's law, notice that I didn't write this as a vector. Coulomb's law, we just find the magnitude of the vector. So there's no directions involved here. So in fact, when I'm using the charges, I'm going to take the absolute value of those charges. You'll see that when we start doing problems. So you don't include a negative or positive sign. Well, you assume them all to be positive. You just take the absolute value. All right, let's do a little bit of vector stuff. So we have two or more charges. You can determine the force, the net force on one of the charges, just by adding up the forces from the other two charges. Let's show you. So say, for example, I have this set of charges, and I want to know what is the net force on Q3. I have two forces acting on Q3. I have the force due to particle 2. What direction is that? So I have a force on this particle that's due to this particle. What's the direction going to be? Left or right? Right, it's going to be to the left because opposite charges attract. This is the force on particle 3 due to particle 2. What about the direction of the force due to particle 1? It's going to be to the right. F due to 3, on particle 3 due to particle 1. So I have two forces acting here. I have F31 and F32. So if I want to know the net force, I just want to find the magnitude of those two forces using Coulomb's law, and then I can just take the vector sum of them. So I can say, can use Coulomb's law to find F31. That's going to be K, which is 9 times 10 to the ninth, times, let me write Coulomb's law here. So Q3 is 4 coulombs. Q1 is 2 coulombs, divided by the distance between them. And the distance between Q3 and Q1 is 3 meters squared. So that is equal to 8 times 10 to the ninth newtons. I remember I told you these aren't very realistic numbers. Look at this force that came out. It's huge. What about this is not very realistic? The charge. Right, the charges are very large. I was just trying to make the numbers easy. But when you see problems, the charges will be smaller. Nano coulombs usually. Alright, so F31 is 8 times 10 to the ninth. And then likewise I can find F32. See, what was Q2? Okay, it's negative 1 coulomb, but I'm just going to write it as 1 coulomb. Alright, so I leave out the sign, divided by the distance between them, which is 2 meters squared. Let's see, that's 9 times 10 to the ninth newtons. So if I want to know my net force, it's going to be 8 times F31 minus F32. That's equal to 8 times 10 to the ninth minus 9 times 10 to the ninth equal to negative 1 times 10 to the ninth. Alright, so that's my net force. What is the direction? To the left or right of that force? What's the direction? Right, it's in the negative x direction to the left, so it's negative 1 times 10 to the ninth newtons. Did that jog in your memory a little bit on vectors?
So this would be like a sum of the or like a equal, in a sense, equilibrium problem?
Mm-hmm. Yeah, you're just adding up vectors. I mean, once you determine your magnitudes, it's just like all the other vector problems that we've done. All right. Honestly, though, on your exam, it's not going to be a one-dimensional problem, most likely. It'll be a 2D problem, which we're going to do right now. Okay? Let's try that out. If you have trouble with this, we spent a lot of time on vectors last semester, but I understand that it, might have lost some of that over the break. So if you have trouble with it, just let me know. I can give you some extra practice so I can sit down and help you with it. All right, so here I have a collection of charges, and I want to know the force on Q3 again. My first step will be just to label all the forces, and then I want to determine the appropriate angles. Okay. So how many forces do I have acting on Q3? No, there are 2. I have 3 particles, and so 2 particles are exerting forces onto Q3. I have the force on Q3 due to particle 2 is going to look like that. I know that it's to the left. Why do I know it's to the left? I have a positive and a negative, so they're going to be attracted to one another. So F32 is to the left, and F31 is up and to the right, like this. All right. At this point, I like to draw my coordinate system. You can do it how you like. I'm just going to draw it on the figure. So I have a coordinate system there. Draw this in. I want to know now what is this angle, and I'll call it theta. Okay? Because remember, I'm going to find the magnitudes of those 2 vectors, and then I'm going to have to find the x and the y components of F31, and then I'll add the x components, I'll add the y components, and then I'll find the resultant magnitude and direction of that final vector. Because I'm looking for the magnitude and direction of the force on this particle. Y'all look really excited about this. Is that true? Like you feel the way that you look? Really excited? Okay, so vectors are very important in physics because a lot of things are vector quantities. They have both direction and magnitude. Alright, so I want to know that angle theta. If I look at this triangle right here, you should see that this angle is the same as this angle right here. So those two angles are the same because I have two lines that are crossing one another. And so this angle is equal to that angle. I forget what's that called. Complementary angle? Yeah, okay. So I have this triangle, 4, 3. I want to know this angle theta. So I say theta is the inverse tan of 3 over 4. I think that's 37 degrees, isn't it? Pretty sure it is. 37 degrees. Alright, so this is equal to 37 degrees. Now I also need to find my magnitudes of F31 and F32. You're just going to use Coulomb's law on this. So see, these problems are identical to ones that we've done before. This is the only difference, is that we're using Coulomb's law. I'm just going to write out the numbers here. 9 times 10 to the 9th, that's K. By the way, that K value is on your equation sheet, as is Coulomb's law. So I would print that out, or I think it might be in the back of your book. Is that true? Is the equation sheet on the back? It is, okay. So you can just sort of keep that handy. We need Q1, which is 3 nanocoulombs. Q3, which is 1 nanocoulomb. That's 10 to the minus 9 coulombs. Divided by the distance squared. This is 5 meters. So it's over 5 squared. I got that 5 meters. I got it because it's a special triangle. It's a 3, 4, 5 triangle. I often use special triangles in the exams just to make them a little easier, so it behooves you to know those things. But if you forget, you can find that resultant, if you remember. The square root of 3 squared plus 4 squared is equal to 5. It's Pythagorean here. I know this is fast, but we've done all this before, so. I can find that. Let's see, that goes away with that. So it's 27 over 25 times 10 to the minus 9. 1.08 times 10 to the minus 9. Similar way I can find F32. That's Q2, Q1, divided by 4 squared. That cancels with that. It's 18 over 16. 1.125. Don't worry, there's some homework problems just to practice this. You'll find some problems like this in the old test too. And I have some clicker questions you can practice as well. Alright, so now I have the magnitudes. I'm going to redraw this. We'll just put in the numbers. I have F31 and F32. F31 was up in this direction. It's 1.08 times 10 to the minus 9 newtons. And it's at 37 degrees. And then F32 is in this direction. 1.125 9 newtons. What do I do next? I want to add up those two vectors. How do I add them? What's that? That's right. You want to take the cosine of 37, find the x and y components of that vector. So anytime I have vectors that are not on axis, like this one, I want to find the x and y components. Now remember this a bit? This easy for you? Yeah. Questions? Kind of? Okay. Is it difficult? It'll really come in practice. You'll need to practice this. So I find the x and y components of this vector. That is F31. So I'll say F31, the x component, is 1.08 times 10 to the minus 9 times the cosine of 37 then F31Y sine of 37. If you run out of space, guys, there's another sheet of paper after this, so if you want to flip the pages. You get 8.625 times 10 to the minus 10. I'm going to keep more sig figs than I need right now until we get to the end. And 6.5 times 10 to the minus 10. So those are my x and y components of F31. So now I'm going to redraw this. Again, you can flip to the next page if you like. And the x component is 8.625. And the y component is up 6.5 times 10 to the minus 10. Alright. So what I want to get to is an x and a y component of my final vector. So right now I have two x components. So I'm just going to add these two together. I'm going to say 8.625 minus the 1.125 times 10 to the minus 10. So I combine these two vectors right here. If I take the difference in those, I get 7.5 times 10 to the minus 10. So my new vector is 7.5 times 10 to the minus 10. And up here, it's still 6.5 times 10 to the minus 10. Alright, so I'm almost there. All I need to do is find the magnitude and direction of those two vectors. So I like to redraw them as a triangle to remind you that we're just doing trig here. Remember, I can move that y component vector over like this. And then my resultant vector is here. I want to know the magnitude of this force, and I want to know this angle. I'll call it P. Okay, so the magnitude of that force is from the Pythagorean theorem. Yeah. Have a mistake somewhere?
1.125 supposed to be to the negative 9.
Is it to the negative 9?
I believe it was the negative 9 from top. Change it again.
Is that right? Yeah. Okay. Well, goodness, that's going to change our numbers, isn't it? I'm sorry. So this should be negative 9. Does everybody agree on that?
Mm-hmm.
Do you think it was funny to let me go ahead?
We're going to let you go away there.
We're going to get that joker. All right. So that changes it quite a bit. I'm sorry about that. But I'm glad to be able to provide some form of entertainment for you. Yeah, that makes it in the negative x direction. Okay, yeah, so it's going to be a little bit different, or quite a bit different actually. It's going to be in this direction now, 2.625 times 10 to the minus 10. Is that better? That's what y'all got? Which changes this to 2.625 10 to the minus 10. I guess I should just look at my notes right here. No, my notes are not correct actually, so changes this triangle as well. It looks like this now. I'm looking for this angle phi. Alright, so my magnitude comes out to 7 times 10 to the minus 10. And my angle phi is going to be the inverse tan of 6.5 over 2.625. The 10 to the minus 10s cancel, so I just leave those off. I get 68 degrees. So my final answer would be this magnitude, 7 times 10 to the minus 10, at 68 degrees above the negative x-axis. Alright, there's a lot of steps. I know we've done this before though, so hopefully those sort of come, if not second nature, that they come with a little prodding. It might take a little bit of practice. There is a homework problem that's very similar to this. We'll also get into this in fields. We won't go through the full blown out all the vectors and stuff, but you could very well have to do it on your exam, which comes up soon, right? I mean, it's just a week or two. Is that right? When's the exam? Okay, yeah, not next week, but the week after. So make sure y'all are keeping up with your homework. That'll be the best way to do well in the class, is that you're keeping up with things along the way. All right. Any questions about this? I know that's really exciting, but it's important to know how to deal with vectors, and especially if you're doing any sort of standardized test too, that always comes up there. It'll come up next chapter as well. All right, let's just try some sort of qualitative questions. We have this configuration of charges. Which vector best represents the net force acting on the rightmost charge? Yeah, so on that plus 2q with all the arrows coming out of it, which of those vectors best represents the force acting on it? Stop at 1 minute. Okay, very good. Y'all got this down, huh? Good to go on this? Let me show you. So I have two forces acting on it. Due to this charge, that force is going to be in this direction. Due to this charge, that force is going to be to the left, but it's going to be twice as big, so it's going to look like this. All right, when I add those two charges together, those two forces together, it'll give me this in this direction. Because the negative, the black charge is a lot, or the black force is a lot bigger than the right arrow. Right. We'll see some more questions like that. What I'm thinking, we want to do this. I'm not too excited about it. It's basically the same as what we had before, but y'all feel like you need extra practice on it? Huh? I'm not letting you out now. Sorry. Listen, my concession used to be in this class. It seems like I let them out like 5 minutes early, like every day. But I decided I didn't do that last semester. I don't know if y'all noticed. Like I decided that was very poor use of time. And y'all come here, and I should just let y'all out one day and just keep you 5 minutes, that extra 5 minutes every day, right? But so anyway, the reason we're doing those 5 tests and they're going to be longer and y'all get extra time is because I vowed to keep y'all the entire time every day. Yes, that's a vow that I've taken. But it's for you because y'all come here. If you're what's 5 minutes if you're gonna be here the whole time? So,
It's a good question. Yeah, I don't know. Maybe I'm just like saying it's still really cool. When you on the last problem you did,
yeah,
you got 3 times 10 to the negative 9.
I got what?
Up at the top when you first started. 3 times 10 to the negative 9.
Oh, the Nano. They're Nano Coulombs. You can't see it very well because I covered it up, but yeah, the charges here are Nano Coulombs. Okay.
I started writing, I was like, I'll just keep going.
No, you should stop me. So this was an old test question. I feel like you need extra practice on this. Not yet. I'm gonna skip this, okay? And maybe if we feel like it, y'all can take a look at it. Maybe we'll come back to it. I'm certainly okay coming back to it, but it takes a while to do. But John should try this one. This was a multiple choice question. What is the magnitude of the force on the 6 nanocoulomb charge? Let me zoom out a little bit. If you have the book, it's in there. See that? You can't see that, can you? There we go. What is the magnitude of the force on the 6 nanocoulomb charge here? The 3 nanocoulomb and a negative 6, what's the magnitude of the force? If you finish that one, I'm going to ask you also what is the direction. So let's think about the direction. what's the answer to the magnitude? Oh, right, yeah, almost done. So I'll stop at 350 or 355 for the magnitude, right? Okay, so this is for the magnitude. The next question is going to be about the direction. Y'all clear on that? Right now I'm waiting for the answer to this question. Okay? It's going away. I'll stop at 410. Okay, good. A is the right answer. You should be able to do that pretty quickly though, okay? Under 2 minutes you should be able to do it. So the force is equal to K Q1 Q2 over R squared. I don't know R right off, so I need to figure out what this distance is. That's going to be the square root of 0.5 squared plus 0.5 squared, which is what, 0.71 meters. So that's 9 times 10 to the 9th times 3 times 10 to the minus 9 times 6 times 10 to the minus 9 over 0.71 squared. Of course, 0.71 squared is 0.5, right? And so that's equal to this answer, 3.2 times 10 to the minus 7. Go ahead and give me the direction as well. What is the direction of that force? It's one of these options. 37 above the negative x-axis, 45 degrees from the positive x-axis, 135 degrees from the positive x-axis, or 20 degrees above the negative x. You shouldn't have to calculate this. You should be able to look at it and tell what the answer is. Alright, I'll stop in about 5 seconds. I'll stop at 55. I'll stop at 1 minute. Five seconds. Alright, over the board there. C's the right answer. Remember guys, on your you need to be careful with your axis that you're measuring from. 45 degrees from the positive x, that would be this angle. Well, look, that's from the negative x-axis. So to make that one right, it would have to say negative x. So that's not correct. It's 135 degrees. So if I draw my coordinate system here, this angle is 135 degrees. If you don't remember all that business that we talked about in our Cartesian coordinate system, I want to revisit that from last semester, or come see me, I can help you with it too. If you're having trouble with vectors, now's the time to deal with it. Y'all have a great day, okay? Have a good weekend. I'll see you Monday.